In the very first moments, the universe is not yet a sky. It is a restless sea of energy, smoothing and sharpening at the same time. Then space stretches, heat thins, light begins to travel free, and from that quiet release a timeline unfolds, from inflation to the first atoms, from first light to the first stars, from a dim cosmic web to the first galaxies taking shape along invisible filaments. Tonight's journey moves slowly, calmly, with clear checkpoints that settle the mind while the cosmos deepens in the background. If this kind of long-form space storytelling helps you unwind, please like this video and subscribe to Space Dreams Documentary. It supports more peaceful documentaries like this one made for rest, wonder and quiet nights. The universe begins before stars. It begins before atoms. Light cannot yet travel freely and space changes shape in a way that resists easy intuition. The opening fact stays calm and clear. Space itself expands extremely fast in its earliest moment, and that expansion leaves a quiet blueprint for everything later. A first scene settles into a uniform darkness with no landmarks. Then a faint grain appears across it. It is not dust or smoke. It is a slight unevenness in density spread everywhere at once. What begins as a whisper at the smallest scales becomes a pattern larger than any later galaxy. The first small unlock arrives without strain. Even perfect smoothness would stay smooth, so structure requires tiny differences to start. The story of first light begins with differences that are almost too small to name. The first core idea is inflation. Inflation is a brief burst of extremely rapid expansion. In plain terms, it resembles a crease in fabric pulled flat in an instant. The crease does not vanish. It is redistributed into a wide and gentle bend. It matters because this stretching sets both smoothness and the first seeds of structure. A second scene slows the moment down. A thin, glowing film fills all space. The film is pulled outward. Tiny dimples on its surface widen and soften as the sheet stretches. Density gradients flatten. Sharp edges turn into broad slopes. The breathing rhythm stays simple. The picture moves from a point-like beginning to a volume that grows without needing a center. Another small unlock arrives. Inflation makes far regions share the same calm starting conditions. Uniformity becomes an outcome rather than a coincidence. The second core idea is fluctuation. A fluctuation is a tiny temporary change in a field or density. It appears and fades like a brief ripple on still water. It is also like a momentary puff in a quiet fog. It matters because those ripples become the long-lived map of where matter later gathers. During inflation, those ripples stretch into wide, shallow waves. A third scene tracks the waves as if seen from above. Broad bands of slightly higher density drift across a dark plane. Between them, slightly lower density forms long, soft troughs. No band is sharp. Each boundary fades like a shadow that thins rather than cuts. A gentle payoff follows. When a wave is stretched beyond the reach of quick causes, its shape stops evolving for a while. It becomes a stored outline rather than an active motion. A quiet image supports this. A surface of water grows wider while its ripples seem to pause in place. The ripples are not frozen by cold, they are frozen by scale. The scale shift stays gentle. A quantum-sized tremor becomes a horizon-sized contour. A third small unlock settles in place. Once stretched beyond a certain size, these patterns stop being erased by local chaos. The third core idea is the horizon of influence. The horizon of influence is the distance a signal can cross in time. In ordinary experience, a boundary like this grows steadily. In the early universe, the boundary competes with expansion itself. It matters because it defines what can share causes and what can only match by earlier shaping. A fourth scene places a soft ring in the dark. Inside the ring, conditions can be coordinated by travelling signals. Outside, the ring conditions remain beyond direct contact for a while. Light behaves as a messenger, with a speed that cannot be exceeded, and the messenger meets space that keeps stretching. Another small unlock arrives here. Inflation lets distant regions match. Without late communication, because the match is set before separation becomes enormous. In that region, temperature is not a flame or a colour. It is the energy of particles and radiation packed into a tight volume. As space expands, that energy thins. A fifth scene shows the early universe as a luminous fog. It is brighter in some patches and dimmer in others. The gradient is smooth, like warmth fading across stone after sunset. Expansion cools the fog by giving it more room. Cooling does not mean cold in any familiar sense. It means less energy per particle and less pressure per volume. A quiet payoff comes next. Those pressure differences later drive waves that leave an imprint in the afterglow. That imprint is subtle. It is more like a faint mottling than a picture. A limit of observation appears naturally at this point. There is no direct view of inflation itself. For a long time after inflation ends, the universe stays opaque. Charged particles scatter light again and again, so any early signal is mixed into a glow with no sharp memory. What remains is indirect. It is a later pattern in light and matter, like footprints left after a moving tide recedes. Reconstruction depends on models and on the resolution of what can be measured. Several different inflation stories can mimic the same broad features, so certainty is never absolute. That limit stays soft and honest. Even so, the surviving pattern is stable enough to guide the story forward. After inflation ends, expansion continues at a calmer pace. The stretched fluctuations remain as gentle hills and valleys in density. Gravity has little time to deepen them yet. A sixth scene lingers on a vast dark landscape made of almost nothing. The hills are not rock. There are slight differences in how much matter fills each region. The slopes are wide and shallow. Nothing tumbles, nothing flashes, yet direction exists. Matter drifts down gradients. Over time, the shallow hills become channels and filaments. A final small unlock settles the opening promise. The blueprint is not a drawing, but a set of gradients that quietly steer what forms. A last scale shift closes the circle. The beginning occupies less than 1 second shorter than a single heartbeat. The consequences stretch across hundreds of millions of years, like a coastline changing grain by grain. Across that span, the faint hills become filaments. Filaments feed the first star-forming clouds. The first stars ignite and begin to alter their surroundings. The opening imprint remains hidden in their arrangement and in the later afterglow. The transition stays gentle. The next section moves closer to the hot opaque plasma that follows inflation, where light scatters and time starts to slow into longer chapters. The early universe stays bright, yet it stays hidden behind its own fog. The key reason is simple. Charged particles fill space and scatter light so often that travel becomes a slow shuffle. A first scene forms as a thick glowing mist with no sharp edges. Light tries to pass through it. Each attempt ends in a soft deflection. The mist is not made of droplets. It is a sea of electrons and protons mixed with radiation. In that region, light behaves as a restless flutter. It changes direction again and again. The first small unlock arrives quietly. Opacity does not require darkness. Opacity can exist inside intense brightness, because direction is lost. The first core idea is a plasma. A plasma is gas, with free charges moving independently. It resembles a storm of tiny grains in constant motion. It resembles flour suspended in air after a gentle shake. It matters because free charges are excellent at turning straight paths into random walks. A second scene slows down into a close view. A single photon moves a short distance. It meets an electron. The encounter changes its direction and slightly shifts its energy. The physical detail stays clear. The scattering is not a collision like hard spheres. It is a deflection by an electric field that has no solid surface. A faint halo appears around every bright region built from countless small turns. Another small unlock follows. When scattering is frequent, a photon does not flee. It diffuses like a scent spreading through still rooms without a direct breeze. The second core idea is the mean free path. Mean free path is the average distance between scatterings. In ordinary air it can be long. In this early plasma it is tiny compared with cosmic scales. It matters because a short mean free path traps information. It smooths sharp features and it delays any clean signal. A third scene shows the effect as layering. Near a denser patch the fog thickens. The boundary is a gradient, not a wall. Light fades as it enters and it brightens as it leaves. The gradients are gentle like warmth moving across a blanket with no seam. A calm payoff arrives. Because light is trapped matter and radiation behave like a coupled fluid. Pressure in radiation pushes back on compression in matter. The third core idea is acoustic waves in the primordial fluid. These waves are pressure ripples travelling through plasma. They resemble sound ripples in water, but the restoring force includes radiation pressure. They resemble a slow tremor across gelatin. It matters because these ripples set a characteristic scale for later patterns. A fourth scene presents the waves from far above. Concentric rings spread outward from a slightly denser spot. The rings are not visible light rings. They are alternating shells of slightly higher and lower density. Each shell has a soft edge. Each shell drifts outward while the whole medium expands. A small unlock settles into place. Expansion does not erase the waves instantly. Expansion stretches them, and cooling slowly reduces their vigor. The single main number appears gently here. About 380,000 years pass before light finally begins to travel freely. That span is like waiting through several human lifetimes, yet it happens while the universe is still very young. The scale shift remains smooth. The same story is described at the level of a single scattering. It is also described at the level of a horizon-sized fog. A fifth scene keeps the breath slow. A vast volume glows nearly evenly. Within it, faint mottling drifts. Nothing has a hard outline. The mottling is only a few parts in 100,000 in temperature. The difference is like the warmth difference across a large room after one brief draft. Another small unlock arrives with that. Such tiny contrasts are enough. Gravity amplifies them later, but only if they survive this opaque era. A limit of observation enters softly. This plasma phase cannot be seen directly with ordinary light from earlier times. Any earlier photon is scattered so many times that its original direction is lost. The earliest view that survives is the moment when scattering finally becomes rare. Even then, the imprint is blurred by the finite thickness of the last scattering layer. That thickness acts like a soft brush. It limits sharpness in the reconstructed map. Measurement also faces limits from foreground emissions that must be removed and from the resolution of instruments that can only sample so finely. Certainty relies on comparing models to patterns rather than watching events unfold. The story stays calm within that boundary. A sixth scene returns to the fluid itself. In denser regions, the plasma presses inward. Radiation pressure pushes outward. The balance creates oscillations that rise and fall like a breathing motion. Each cycle leaves a slight preference for certain separations, like spacing marks on a long tape laid down by repeated gentle tapping. A final small unlock forms. The trapped light does not vanish. It stores a memory of these waves in its temperature pattern. Later, when the fog clears, that memory appears as a faint mottled glow across the sky. The closing motion eases forward. Cooling continues. Charges begin to bind into neutral atoms. Scattering weakens. The next section moves toward the thinning of this bright fog and toward the first free paths of light. Clarity arrives slowly, not as a switch, but as a thinning of a luminous haze. The reason is plain. As the universe cools, electrons begin to bind to protons and scattering falls away. A first scene appears as a bright fog filling all directions. The fog has depth. It has layers with a gentle gradient from slightly denser to slightly thinner. In that region, light behaves as a wandering spark that keeps being turned aside. Each turn softens edges and erases direction. The first small unlock comes calmly. Light is not freed by distance. Light is freed when free charges become rare. The first core idea is recombination. Recombination is electrons joining protons to form neutral hydrogen. It resembles a room of loose confetti settling into pairs that stop swirling independently. It resembles grains that cling together after humidity rises. It matters because neutral atoms scatter light far less than free electrons do. A second scene slows toward the boundary where this change happens. The fog does not peel away as one sheet. It becomes a translucent band with thickness. Within that band, some photons still scatter. Others slip through. The physical detail stays concrete. The band has a front edge and a back edge. Between them lies a soft transition like frost melting across a window without a sharp line. Another small unlock settles. The first light that later survives is not emitted for the first time. It is released for the first time. The second core idea is the last scattering surface. Last scattering surface is the layer where photons scatter one final time. It resembles a thin curtain that becomes transparent as threads loosen. It resembles the final turn in a maze where a straight corridor suddenly opens. It matters because that layer defines the oldest image carried by light. A third scene presents the layer as a dim shell surrounding everything. It is not a solid wall. It is a region with depth where scattering still happen, but with growing gaps. A photon's path is no longer a tight zigzag. It becomes a long stride with only occasional deflections. The shell has mottling. It has small warm and cool patches. Each patch has a soft edge. Each patch is a temperature gradient rather than a boundary. A quiet payoff arrives. Those gradients are the frozen record of earlier pressure waves. They become the faint pattern later seen as the microwave background. The main number rests here. The release happens about 380,000 years after the beginning, like an age measured in several lifetimes. The comparison stays gentle. In cosmic terms, it is still early, like the first morning of a long year. The scale shift remains smooth. A single electron binding to a proton changes a cross-section. That change alters the transparency of the entire universe. A fourth scene carries the transparency outward. The fog thins. The glow does not end. It continues, but it becomes an afterglow that can travel. Light spreads in straight lines across growing distances. The scene is quiet. It is a vast dark volume with a faint uniform shine and small dimples in brightness. Another small unlock arrives without emphasis. Once scattering fades, information can travel. Direction becomes meaningful again, and patterns can persist across space. The third core idea is redshift. Redshift is stretching of light to longer wavelengths by expansion. It resembles a rubber ribbon marked with stripes being pulled so the stripes spread farther apart. It resembles a note sliding lower as a vibrating string is slowly lengthened. It matters because first light does not stay bright and hot. It cools into microwaves while it travels. A fifth scene lingers on that cooling as a change in texture. The glow becomes softer. The energy per photon drops. The whole sky becomes a uniform field with delicate mottling like faint marbling. The mottling stays, but it shifts into longer, quieter wavelengths. A gentle payoff follows. The afterglow carries a nearly uniform temperature. The tiny deviations encode the seeds that later guide matter into filaments and galaxies. A limit of observation enters softly. The last scattering layer has thickness. That thickness blurs fine detail like viewing through a thin veil. There is also a fundamental limit from the finite size of the observable region, which makes the largest patterns uncertain. Some scales are sampled only a few times across the sky, so statistics become noisy. Even perfect instruments cannot avoid that sampling limit. Model inference also depends on separating the afterglow from later emissions that lie in the way. The story remains steady within those bounds. A sixth scene returns to the geometry of the shell. At this distance, the last scattering surface forms a sphere around any point. The sphere is not centered on a place in space. It is centered on the act of receiving light at a moment in time. The sphere expands outward as time passes, not because it moves, but because older light is seen from farther away. The physical detail stays clear. The shell has a faint ring-like imprint in its statistics. That imprint comes from a preferred scale set by early sound waves. Another small unlock settles in. The same physics that traps light also sets a ruler. When the ruler is read in the sky, it reveals how space has expanded since then. The closing motion eases into darkness again, but now a transparent darkness. Matter remains. Light moves freely. The next section drifts into the long, quiet era that follows, when no stars shine yet, and gravity begins to work on the stored blueprint. After first light begins to travel, the universe grows quieter in appearance, yet busier in structure. The key change is simple. Light streams freely while matter starts to drift under gravity with fewer restraints. A first scene settles into a deep, transparent darkness filled with a faint afterglow. The glow is even, but not perfectly. Small gradients remain like a soft marbling spread across an endless surface. In that region, light behaves as a clean messenger that no longer loses direction at every step. The first small unlock arrives gently. Transparency does not create new matter patterns. It reveals which patterns already survive and can now evolve. The first core idea is decoupling. Decoupling is matter and radiation no longer strongly influencing each other. It resembles a warm breeze that finally stops pushing on falling leaves. It resembles a drum beat fading until dancers move by their own balance. It matters because gas is no longer held up by radiation pressure as strongly as before. A second scene moves closer to the gas itself. Neutral hydrogen fills space thin as an almost perfect vacuum. Tiny clumps appear as slightly denser regions with soft edges. Each clump has a boundary that is not a wall. It is a gradual slope where density rises then eases back down. Another small unlock follows. Once the pushing force weakens, gravity does not need much time to amplify small differences. The second core idea is a dark matter halo. A dark matter halo is an invisible mass clump that shapes gravity. It resembles a shallow bowl that guides beads toward its center. It resembles a gentle dimple in a stretched cloth where grains tend to collect. It matters because ordinary gas tends to fall into these bowls even when the gas itself is very thin. A third scene places these bowls into a wider view. Filaments of mass stretch across darkness like faint strands of smoke, but without any glow. At the intersections, halos sit like knots. Around each knot, gas forms a slightly denser envelope, with a smooth gradient thicker toward the middle. The physical detail stays concrete. Infall creates motion that is not chaotic. Gas streams inward along preferred directions like slow currents, converging into a basin. A calm payoff arrives. The earliest web of structure grows mainly by deepening existing slopes, not by creating sharp new boundaries. A fourth scene slows to a single parcel of gas approaching a halo. Compression warms it, but expansion and radiation cooling lower its temperature overall. The balance is gentle. The gas does not flash. It changes state by slow pressure adjustments and gradual densification. The main number enters quietly. About 100 million years pass before the first stars begin to ignite. That span is like a long season that allows subtle changes to accumulate into a decisive shift. This scale shift stays smooth. A motion that begins as a slight drift across a vast region becomes a decisive inward flow near a halo center. Another small unlock settles in. The first stars require not only gravity but also a way for gas to shed heat and keep collapsing. The third core idea is cooling by simple molecules. These molecules are small combinations that radiate energy efficiently. They resemble a faint valve that lets warmth leak away from compressed gas. They resemble a thin mist that carries heat off as invisible light. It matters because cooling allows the densest cores to tighten further instead of stalling. A fifth scene shows the early collapse as layered structure. Outer gas forms a broad, slow rotating sheet with a gentle spiral pattern. Inner gas forms a denser core with a sharper gradient. The boundary between them is not a line. It is a thick transition zone where density and temperature shift gradually. Another small unlock arrives with that layering. Rotation can delay collapse at large radii, yet still permit collapse at the centre, where gradients steepen. The rhythm remains steady. The story passes a checkpoint. First a halo forms, next gas gathers into it, then gas cools enough to shrink its core. A sixth scene holds on the darkness between halos. It remains almost empty. The afterglow light continues to stretch and cool as it travels. The sky becomes quieter in brightness but richer in hidden contrast. At this distance, a signal would cross immense spans without meeting much matter at all. Another small payoff arrives. The Dark Ages are not empty. They are transparent to light yet full of mass that quietly rearranges. A limit of observation appears softly and clearly. This era produces little visible light. Direct images are not available in the usual sense. Reconstruction relies on indirect traces. One trace comes from the afterglow pattern which sets initial conditions. Another comes later from how neutral hydrogen absorbs or emits faint radio signals. That approach faces strong obstacles. Foreground radio emission from later cosmic sources can overwhelm the faint imprint. Resolution limits also matter because the relevant structures can be smaller than the coarsest beams. Inference depends on careful modelling, and different assumptions can mimic similar signals. The limit stays calm. Even without direct pictures, the physics of gravity and cooling remains consistent enough to outline the path forward. A seventh scene returns to a forming filament. Gas streams along it as a slow ribbon thicker in the middle. The ribbon has a tapered edge where density falls off smoothly into near emptiness. Where two ribbons meet, the flow bends. It curves inward and thickens into a knot. The knot develops a subtle, shadow-like gradient in temperature warmer toward the densest centre. Another small unlock arrives. Filaments do not merely connect halos. They feed halos with a steady supply of gas shaping where collapse becomes most likely. A final scene narrows to the innermost region of one halo. The core becomes denser and more shielded. Cooling becomes more effective there. The gas begins to fragment into smaller condensations like a slowly thickening syrup that starts to form separate droplets under gentle stirring. The droplets are not stars yet. They are precursors regions where gradients steepen and collapse accelerates. The section closes with a soft transition. The next section moves into the threshold where these dense cores tip into runaway collapse. First starlight begins to appear in small pockets, and darkness changes locally without haste. The first stars begin as quiet knots inside darkness where gas finally loses its ability to resist collapse. The central reason is steady. Cooling lets a dense core shrink until gravity dominates, and a new light source can form. A first scene holds on a single halo's centre. A soft spiral of neutral gas turns slowly. The outer layers remain thin and broad. The inner layers thicken into a rounded core with a steepening gradient. The boundary between layers stays smooth like shade fading into shade on a curved stone. A first small unlock arrives gently. Collapse is not triggered by a sudden push. It begins when heat escapes faster than pressure can rebuild. The first core idea is runaway collapse. Runaway collapse is shrinking that speeds up as density rises. It resembles a snowball rolling downhill that gathers more snow yet without any jolt. It resembles syrup thinning as it warms, so it pours faster the more it flows. It matters because once the core tips past a threshold, the change becomes self-reinforcing. A second scene moves closer into the core. Gas becomes denser toward the centre. The gradient steepens into a tighter bowl. Motion is not chaotic at first. It is an inward drift, with a slight twist from rotation. The physical detail stays clear. As infall continues, a flattened disk forms around the densest point. The disk has an edge that is not sharp. It is a tapered rim where density falls off smoothly. Another small unlock follows. A disk is not an ornament. It is a way to store rotation so that matter can still reach the centre. The second core idea is fragmentation. Fragmentation is splitting into smaller collapsing pieces. It resembles a thick cloud that cools and breaks into separate droplets. It resembles a slow cracking of mud as moisture leaves it and separate plates appear. It matters because it decides whether one star forms or a cluster forms. A third scene shows fragmentation in a calm way. The disk and inner envelope develop faint clumps. Each clump has a core and a surrounding skirt of lower density. The clumps drift and merge or drift and separate depending on local gradients. The scene stays quiet. No sharp flashes. No sudden boundaries. A small payoff arrives here. In primordial, gas fragmentation can be limited because cooling channels are few. That favours fewer larger clumps rather than many small ones. The third core idea is radiative cooling by simple molecules. These molecules are simple and rare yet effective at shedding heat. It resembles a thin vent that lets warmth leak out of a sealed room. It resembles a faint whistle of energy leaving without changing the room's shape. It matters because without cooling, the core would stall before reaching star-forming densities. A fourth scene shifts to the centre, where the densest clump becomes opaque to its own cooling radiation. The core develops a warm interior. Around it sits a cooler shell. The shell acts like insulation. Heat tries to escape. It leaks out more slowly. The temperature profile becomes layered warmer in the centre and cooler outward. Another small unlock settles. Starbirth is delayed once again at the very end because opacity returns locally inside the core. The main number appears softly. The collapse of a dense core can complete in about 1 million years, like a long quiet night compared with the earlier 100 million year wait. The scale shift stays smooth. A process that seemed frozen across cosmic distances becomes a rapid change inside a single small region. A fifth scene keeps the image tangible. A tiny region at the core becomes so dense that pressure rises steeply. Infall continues onto the disk. The disk feeds the centre. The centre becomes a protostar, a hot compact object not yet shining like a mature star. The protostar has a boundary where gas becomes fully compressed and heated. That boundary is not a surface like rock. It is a region where density and temperature rise sharply over a small distance. Another small unlock arrives. A star does not begin with fusion immediately. It begins with gravity converting infall energy into heat, building the conditions that make fusion possible. A limit of intuition and observation enters softly and clearly. This first generation is difficult to witness directly. The light is scarce at first, and it is easily absorbed by surrounding gas. Later, when light grows strong, it changes the environment that created it. That feedback makes the original conditions hard to reconstruct. Models must infer masses and formation rates from indirect signatures, and different assumptions can produce similar outcomes. Resolution also matters. The earlier star-forming regions are small on the sky at extreme distances, so details blur together into a single faint glow. The limit stays calm and the path remains coherent. A sixth scene returns to feedback in a quiet way. As the protostar grows hotter, it emits more radiation. Radiation heats nearby gas. The heated gas creates a pressure gradient that slows infall along some directions. The disk still feeds the centre where it is shielded and dense. This creates anisotropy, a difference between directions. One side clears more than another. Shadows form behind denser clumps. The physical detail is a shifting pattern of bright and dim regions around the core, like light passing through layered fabric. Another small unlock follows. The first stars carve their own immediate surroundings before they brighten the wider universe. A seventh scene widens out. One halo contains a few forming stars. They are embedded like small embers inside a dark nest of gas. Around them, the cosmic web continues to deliver new material. The star-forming region remains a tiny knot in a vast filament. The scale shift remains gentle. A few dense cores smaller than a solar system sit inside a halo larger than any later galaxy's central bulge. The closing motion eases toward the next change. Starlight begins to escape beyond the birth clouds. It meets neutral hydrogen in the wider medium. The next section follows how that light alters the state of the surrounding gas, creating expanding regions of ionization without haste. Starlight begins to change the universe by carving invisible cavities in the surrounding gas. The core mechanism is steady and physical. Energetic light knocks electrons free and turns neutral hydrogen into a thin plasma again. A first scene forms around a newborn star group. A small bright region sits inside a larger dark cloud. The edges of the cloud are soft with tapered density that fades into near emptiness. From the bright centre, a glow spreads outward. It does not fill everything equally. It meets denser clumps and bends around them. Behind those clumps lie shadowed wedges where light weakens. The first small unlock arrives quietly. The earliest cosmic transformation after star birth is not more brightness. It is a change of state in the gas that becomes transparent to certain radiation. The first core idea is ionization. Ionization is removing an electron from an atom. It resembles pulling a bead off a string so the bead moves freely. It resembles separating pairs in a slow dance so partners drift apart. It matters because free electrons alter how gas absorbs and emits energy. A second scene moves closer to the boundary where ionization is active. The boundary is not a wall. It is a thick front where the fraction of free electrons rises across a gradient. Near the star, the gas becomes more ionized. Farther out, it stays neutral. The physical detail stays clear. The front has a curved surface like a bubble skin. It is brighter on the inside and dimmer outside. The curvature shifts as the front meets denser knots. The front slows where density rises. It speeds where the medium is thin. Another small unlock follows. Ionization proceeds fastest not where light is strongest alone, but where density is lowest, so fewer atoms need changing. The second core idea is a recombination balance. Recombination balance is ionization matched by recombination. It resembles a basin filling from one tap while a drain lets water out. It resembles a candle that melts wax while the wax also cools and hardens again. It matters because it sets the size and stability of ionized regions. A third scene holds on the interior of an ionized bubble. The gas is warmer. Pressure rises. The warmer gas expands outward. It forms a gentle outflow that smooths small irregularities inside the bubble. The bubble's inner edge is clearer than its outer edge. The outer edge remains ragged where dense clumps resist change. A small payoff arrives here. The boundary is not determined only by light travel. It is determined by a tug between photon supply and the rate that free electrons find protons again. The main number arrives softly. A single large ionized region can grow to roughly 10 million light-years across. That span is like a chain of many large galaxies laid end to end with wide gaps between them. The scale shift remains smooth. A single photon changes one atom. Vast bubbles emerge from countless such changes across enormous volumes. A fourth scene widens to the cosmic web. Dark filaments carry neutral hydrogen. At the nodes, galaxies and star groups ignite. Around each node a bubble forms. Some bubbles stay nearly spherical. Others stretch into lobes along filaments. The physical detail is a set of overlapping shells. Where shells meet their boundaries, soften and fade. Neutral regions remain between them like dark lakes between islands of clarity. Another small unlock settles. Ionization is patchy. It is not a uniform wave that sweeps everywhere at once. It advances as separate bubbles expand and merge. The third core idea is the ionization front. Ionization front is the moving boundary between neutral and ionized gas. It resembles a slow tide line that climbs a beach then retreats where the sand rises. It resembles a frost line that advances unevenly across a field with warmer and colder patches. It matters because its shape encodes both source brightness and gas density. A fifth scene tracks one front along a filament. The filament is denser than its surroundings. The front presses into it slowly. A bright crescent forms on the side facing the light source. A dimmer tail trails behind, protected by the filament's column of gas. The front wraps around like water around a rock. The shadow behind the filament persists for a time. Another small unlock appears here. Dense structures can delay ionization locally, while the broader volume becomes ionized. This creates a layered universe where large scales clear first and some pockets remain neutral longer. A limit of observation enters softly and clearly. This era is not easily mapped directly. The ionized gas can be faint and neutral hydrogen signals can be confused by later foreground emissions. The patchiness also makes inference difficult. A small surveyed region may not represent the whole. Resolution limits matter because bubbles and fronts have structure smaller than coarse beams can resolve. Models rely on statistical measures and on indirect absorption features. Different mixtures of sources can mimic similar large-scale patterns. The limit remains calm and the story stays grounded. A sixth scene returns to the interior of a bubble after expansion begins. The gas inside is smoother. Its pressure gradient pushes outward. The bubble's edge becomes more rounded where density is even. It becomes scalloped where dense clumps remain. Thin tendrils of neutral gas penetrate inward along sheltered paths. These tendrils have tapered ends like wisps. Their edges are soft and fading. Another small payoff arrives. The first stars not only illuminate, they reshape the thermal and chemical state of gas, which changes how later stars form. A seventh scene widens again to show merging. Two bubbles drift toward each other as their sources continue shining. Their boundaries touch. In the overlap region, the last neutral pockets thin. The combined region becomes a single larger cavity with a more complex rim. The rim has dents where filaments enter. It has smoother arcs where voids lie outside. The scale shift remains gentle. Local bubbles, each born around a small star cluster, join into regions that span distances beyond a single filament intersection. The closing motion eases forward. As bubbles merge and the patchwork clears, light can travel farther without being absorbed by neutral hydrogen. The next section moves from individual bubbles to the broader progress of rionization and to the quiet emergence of the first sustained galaxies within this changing medium. Reionization advances like a slow clearing of mist, uneven and patient across the cosmic web. The simple truth is steady. Many separate light sources create expanding ionized regions that gradually overlap into a larger transparent volume. A first scene opens on a wide patchwork. Some regions are clear, filled with thin, warm plasma. Nearby regions remain neutral, darker and cooler with denser filaments still intact. The boundary between them is not sharp. It is a thick frontier with a gradient like fog thinning across a hillside where valleys stay hazy longer. At this distance, light behaves as a tide of energetic photons that lose strength as they are absorbed. The first small unlock arrives quietly. Clearing does not happen everywhere at once because density is not uniform, so the same light has different work to do. The first core idea is bubble overlap. Bubble overlap is ionized regions merging into one. It resembles soap bubbles in a sink touching and becoming a larger shared surface. It resembles puddles after rain joining into one sheet as the ground dips connect. It matters because overlap marks the moment when long paths of light open across much larger distances. A second scene narrows to two neighbouring bubbles. Each bubble has a curved rim with scalloped indentations where dense clumps resist ionization. Between the bubbles lies a neutral bridge. The bridge is thin like a ribbon, and it casts a shadowed lane behind it. As both bubbles expand, the ribbon narrows. The rim brightens on the sides facing the light sources. It stays dim on the lee side. Another small unlock follows. The last neutral islands persist not because light is absent, but because recombination and shielding keep rebuilding neutrality in dense pockets. The second core idea is clumping. Clumping is matter concentrated into small dense regions. It resembles a sponge with tight pores where water lingers longer. It resembles a field of tall grass that blocks wind near the ground. It matters because clumps raise recombination rates, and slow the advance of ionization fronts. A third scene moves into one filament. The filament is a long cylinder of neutral hydrogen with a tapered edge. Density is highest at its spine and falls outward smoothly. An ionization front presses against the filament's surface. The front wraps around it like water around a log. The outside layers ionize first. The inner spine remains neutral longer. The physical detail is layered. A thin ionized skin forms, then thickens. Behind denser knots, wedge-shaped shadows persist. A calm payoff arrives here. The cosmic web acts as both fuel and obstacle feeding galaxies, while preserving neutral pockets that delay complete clearing. The main number appears softly. Reionization completes over roughly 500 million years, like a slow sunrise that takes many long mornings to finish. The scale shift stays gentle. A photon changes one atom. Over hundreds of millions of years, countless photons reshape volumes spanning tens of millions of light years. A fourth scene widens again to show the sky as a quilt. Bright sources sit at nodes. Around each node a bubble grows. Some bubbles look nearly round in voids. Others look elongated along filaments like stretched droplets pulled by gravity's threads. Where several bubbles meet the rims soften. The rims fade into a shared interior that is warmer and smoother than the outside. Another small unlock settles. Overlap changes the character of the medium. After overlap, photons can travel farther before being absorbed, so growth accelerates on large scales, even while small neutral islands remain. The third core idea is mean free path of ionizing photons. Mean free path is the typical distance before absorption. In a neutral medium it is short. In an ionized medium it becomes far longer. It matters because it governs how quickly distant regions can be influenced by distant sources. A fifth scene tracks this change as a gradual opening of corridors. Before overlap, a photon's path ends quickly at a neutral wall. After overlap, the walls retreat. Long channels form through voids. Filaments still intrude like dark ribs, but the spaces between ribs become more connected. A small payoff arrives. Once channels open, the universe becomes a medium where rare neutral regions stand out as exceptions rather than the rule. A limit of observation enters softly and clearly. The patchwork is hard to map directly, because most of the action involves faint signals. Neutral hydrogen can be traced through radio wavelengths, yet foreground emission from later sources can overwhelm the faint pattern. Resolution limits also matter. Small neutral islands can be smaller than the beam, so their contrast is diluted. Absorption signatures along single-site lines sample only narrow paths, so they may not represent the whole. Models must combine sparse constraints, and different reionization histories can match similar average statistics. The limit stays calm and the narrative remains physical. A sixth scene returns to a single neutral island inside an ionized sea. The island is denser, cooler, and partly shielded. Its edge is a gradient where ionization fraction rises outward. The edge becomes a soft rind. The rind thickens as photons chip away. The core remains neutral until the rind reaches inward. The island slowly shrinks like a lump of ice melting in warm water, yet without droplets or splashes. Another small unlock follows. The end of reionization is not a final sweep, but the slow disappearance of protected pockets as the background of ionizing light strengthens. A seventh scene shows the background itself. After overlap, a diffuse ionizing field fills space. It is faint but persistent. It sets a baseline that keeps most gas ionized, especially in low-density regions. In that region, a signal would travel farther before being absorbed, and that increased reach changes how quickly the remaining islands erode. The scale shift remains gentle. Local shadows around dense knots persist, yet the global background smooths the large-scale map. The closing motion eases toward the next checkpoint. With the medium increasingly ionized, galaxies begin to shine through longer distances. Their assembly becomes more visible in principle, even if details remain faint. The next section moves into the growth of the first sustained galaxies and into how their internal structure emerges within the cleared and still uneven cosmic web. The first galaxies assemble as dim knots where many streams of gas and small star groups gather into one rotating system. The central idea is steady. Gravity collects matter into halos, and cooling lets gas settle into dense regions that keep forming stars. A first scene opens on a node of the cosmic web. Several filaments converge there like slow ribbons. Each ribbon has a thicker spine and tapered edges that fade into the void. Along the spines, gas drifts inward. It is not a fall like stones. It is a quiet inward flow guided by gradients and gravity. The first small unlock arrives gently. A galaxy begins as an organization of motion, not as a bright shape. It forms when many infalls share a common center and a common rotation. The first core idea is hierarchical assembly. Hierarchical assembly is building large systems from smaller ones. It resembles small droplets on a leaf sliding together into one larger drop. It resembles grains in a shallow tray that drift into a pile when the tray is gently tilted. It matters because early galaxies grow by merging and by steady feeding along filaments. A second scene narrows to the inner region of one growing system. A faint disk of gas forms. The disk is not thin at first. It is puffy and turbulent. It has a thickened middle and a softer outer rim. Density rises toward the center in a smooth gradient. The physical detail stays clear. The disk shows spiral-like shear patterns, stretched arcs where gas streams wrap and mix. Behind denser clumps, darker wakes appear where inflow is shielded. Another small unlock follows. Rotation does not prevent growth. Rotation shapes how gas settles, turning direct infall into a disk that can keep feeding a central region. The second core idea is a gravitational potential well. Potential well is a region where gravity makes inward motion favorable. It resembles a wide bowl where marbles drift toward the lowest point. It resembles a gentle dimple in a mattress where a cloth naturally slides inward. It matters because the depth of the well controls how strongly gas is held and how easily it can cool and condense. A third scene widens to show several small halos near the node. Each halo carries gas. As halos approach each other, their outer envelopes overlap. Tidal forces stretch the envelopes into streams. The streams form bridges that are denser than the surrounding void. The edges of these bridges are tapered and soft. The motion is slow and layered. Dense cores orbit while diffuse gas forms trailing arcs. A calm payoff arrives. Mergers are not only collisions. They are rearrangements of orbits that turn separate inflows into one shared circulation. The main number appears quietly. An early galaxy can span about 10,000 light-years. That distance is like placing many solar systems in a long chain, until the chain becomes a small city-sized island in space. The scale shift remains smooth. A region that is tiny compared with today's large galaxies still contains countless stars and broad reservoirs of gas. A fourth scene holds on star formation inside the growing disk. Dense clouds collect where gas streams intersect. Compression raises density. Cooling lets the densest pockets shrink further. The clouds are clumpy and layered. Each cloud has a denser core and a lower density skirt. The skirts overlap to create soft boundaries rather than sharp edges. A small unlock arrives here. Early galaxies can remain faint not because stars are absent, but because gas and dust-like particles can absorb light locally and re-radiate it in less visible ways. The third core idea is feedback. Feedback is energy from stars altering surrounding gas. It resembles a kettle gently steaming where the steam changes the room's humidity. It resembles a warm draft rising from a heated floor that redirects falling dust. It matters because feedback can slow future star formation by heating gas, yet it can also trigger new collapse by compressing nearby regions. A fifth scene shows feedback without drama. Within the disk, a cluster of young stars brightens. Around it, an ionized bubble forms. The bubble's rim is scalloped by density variations. Pressure inside the bubble pushes outward. It forms a gentle, expanding shell. The The shell sweeps up neutral gas into a thin layer. The layer thickens where it meets denser clumps. Shadows appear behind those clumps. Another small unlock follows. Feedback does not erase structure uniformly. It creates layered environments where some regions clear while others remain shielded and continue forming stars. A limit of observation enters softly and clearly. These first galaxies are faint and distant. Their light is stretched into longer wavelengths by expansion. Many details blur into a single small patch, so internal disks and shells cannot be resolved directly. Inference depends on comparing spectra and brightness profiles to models. Dust and gas absorption can hide the true star formation rate. Sample variance also matters. A few observed galaxies may not represent typical ones, because the brightest are easiest to detect. The limit stays calm and the path remains consistent. Even with uncertain details the global picture holds. Filaments deliver gas, halos merge, disks form, stars ignite. Feedback shapes the next cycle. A sixth scene widens again to the node and its surroundings. The galaxy sits at the intersection like a faint whirl. Streams continue to flow inward along filaments. The galaxy's outer gas forms a halo with a smooth fall-off in density. The halo is not empty. It is a diffuse reservoir that feeds the disk. The halo's boundary is not a line. It is a long taper where gas thins into the void. A small payoff arrives. The early galaxy is not an isolated island. It is a junction in a larger circulation that links many scales. A seventh scene returns to the disk edge. The disk rotates. The outer rim shows shear where inner gas moves faster than outer gas. This shear stretches clouds into elongated shapes. It forms arcs and lanes of higher density that spiral inward. The motion is gentle. The shapes are slow. The scale shift remains steady. The same shear that stretches a cloud over thousands of light years arises from gravity acting over the whole halo. The closing motion eases forward. As galaxies become more common, their combined light and feedback continue to reshape the intergalactic medium. The next section follows how the chemistry of gas changes as heavier elements accumulate, altering cooling and making later generations of stars and galaxies form in new ways. Chemical change begins as a faint seasoning added to an otherwise simple cosmic gas. The early answer is calm. The first heavy elements appear when massive stars end, and their debris mixes into surrounding clouds that later form new stars. A first scene opens inside a young galaxy, where dense clouds cluster along a thick disk. The disk is mottled with bright regions and darker lanes. The darker lanes are not empty. They are denser gas that absorbs light and forms shadowed streaks with soft edges. In that region, light behaves as a gentle flood that is partly blocked by layered clouds. The first small unlock arrives quietly. The universe does not need much metal to change how gas cools. Even a trace can open new pathways for heat to leave. The first core idea is nucleosynthesis. Nucleosynthesis is making heavier nuclei inside stars and explosions. It resembles mixing new pigments into clear water, so future swirls gain colour. It resembles adding a small pinch of salt that changes how ice melts. It matters because new elements provide additional ways for gas to radiate energy and cool. A second scene moves toward a dying, massive star. The surrounding gas is thin. The star's outer layers expand outward. They form a layered shell with a dense front and a thinner wake behind it. The shell has a curved boundary that grows and fades into the background. Within the shell, temperature gradients form. The inner region stays hotter. The outer region cools as it expands. Another small unlock follows. The debris is not evenly spread. It begins as a structured flow with shells and filaments, so enrichment is uneven at first. The second core idea is mixing. Mixing is spreading elements through turbulence and flows. It resembles dye dropped into water, forming curls and sheets before it becomes uniform. It resembles smoke in still air that first forms ribbons and then diffuses. It matters because patchy enrichment creates regions that cool and collapse differently from their neighbours. A third scene lingers on a pocket of enriched gas drifting through a halo. The pocket is denser than its surroundings. Its edge is a gradient where enriched material blends into primordial gas. Small eddies form at that boundary. The eddies stretch the pocket into a thin sheet. The sheet folds and breaks into streaks. The physical detail is clear. The streaks have bright rims where heating occurs and cooler interiors where radiation escapes more efficiently. A calm payoff arrives here. When metals appear, cooling can become more efficient at lower temperatures, so fragmentation becomes easier and stars can form in smaller masses. The main number enters softly. About 1% of the sun's metal content can already change cooling dramatically in many clouds. That tiny fraction is like a single drop of ink tinting a glass of water. The scale shift remains smooth. A slight change in atomic composition inside a cloud can alter the fate of an entire star-forming region. A fourth scene returns to a collapsing cloud in the galaxy disk. Without metals, the cloud tends to stay warm and resist breaking apart. With metals, thin, radiative lines carry energy away. The cloud's temperature gradient steepens. The core becomes cooler relative to the outer layers. The cloud develops many small condensations. Each condensation has a dense center and a softer skirt. Boundaries remain tapered. No clump has a sharp edge. Another small unlock follows. Metals do not merely add mass. They add radiative channels so collapse can proceed deeper before pressure halts it. The third core idea is dust grains. Dust grains are tiny solid particles in space. They resemble fine soot that provides surfaces for molecules to form. They resemble sand that helps moisture collect into droplets on a cool morning. It matters because dust can both shield gas from harsh radiation and enhance cooling by emitting infrared light. A fifth scene shows dust in a quiet way. Within a dense cloud, starlight is absorbed and the interior darkens. The cloud's surface remains faintly lit. Inside, heat leaks outward as longer wavelength radiation. The cloud becomes layered. A warmer outer skin surrounds a cooler core. A small payoff arrives here. Shielding allows molecules to survive and molecules further increase cooling, creating a calm cascade toward denser fragmentation. A limit of observation enters softly and clearly. The earliest metal enrichment is hard to measure directly. Metal lines can be faint and blended. Distant spectra have limited resolution, so different element ratios can look similar. Dust complicates inference by absorbing light and altering apparent brightness. Some enriched gas may be hidden in dense regions that emit little. Models must combine indirect clues from absorption systems and from the properties of later stars. Different mixing histories can produce similar averages. The limit stays calm and the physical picture remains coherent. A sixth scene widens to the intergalactic medium around the galaxy. Outflows from young stars and explosions push material outward. The outflow is not a uniform wind. It forms lobes and chimneys where density is lower. Along those channels, enriched gas travels farther. It leaves behind a trail of slightly higher metallicity that fades with distance. The trail has a gradient like a scent trail that weakens yet without any human presence. Another small unlock arrives. Enrichment is not confined to galaxies. It begins to spread into the spaces between them, changing the cooling properties of future inflows. A seventh scene returns to the cosmic web. Filaments feed galaxies with mostly primordial gas, yet now the gas is no longer perfectly pure. Thin sheets of enriched material cling to some filaments. They form faint layers around denser spines. The layers alter how gas fragments when it later collapses in new halos. The scale shift remains gentle. A grain of dust within a cloud can influence molecule formation. A network of many galaxies can seed large volumes with new chemistry. The closing motion eases forward. As metals and dust build up, star formation becomes more efficient in some regimes and more regulated in others. The next section follows how galaxy structure and light output evolve as feedback cooling and chemistry interact across many generations of stars. Galaxies become steadier when their own light begins to regulate how gas moves and cools inside them. The plain answer is calm. Feedback and cooling compete, and that competition shapes disks, clouds, and the pace of star formation. A first scene opens inside a young galaxy disk. The disk is thick and faintly luminous. Dark lanes cross it like soft brushstrokes. Those lanes are denser gas and dust layered into sheets and filaments. Along their edges, brightness rises where young stars heat nearby material. The physical detail is a gradient. Warm edges fade into cooler interiors. In that region, light behaves as a gentle pressure that can warm, ionize, and sometimes push gas outward. The first small unlock arrives quietly. Star formation is not only a result of gas supply, it becomes a cycle that can slow itself down by heating and stirring its own fuel. The first core idea is regulation. Regulation is star formation limited by its own effects. It resembles a fireplace warming a room until fresh air flows slows as temperature equalizes. It resembles boiling water that creates steam, which then reduces the flame's direct contact. It matters because regulation prevents a galaxy from converting all its gas into stars too quickly. A second scene narrows to a dense cloud inside the dark lane. The cloud is clumpy and layered. A cooler core sits inside a warmer envelope. The envelope is lit more strongly on the side facing a nearby cluster. The far side stays in partial shadow with a softer temperature gradient. Gas flows along the cloud's surface. It streams past like slow current around a rock. Another small unlock follows. Even weaker symmetry and heating can redirect collapse. Shielded pockets can keep forming stars while exposed surfaces erode. The second core idea is turbulence. Turbulence is chaotic motion over many scales. It resembles cream stirred into coffee-making swirling eddies that keep mixing. It resembles wind rippling tall grass in patterns that shift and return. It matters because turbulence can both support gas against collapse and create dense knots where collapse begins. A third scene shows turbulence in the disk as a layered motion. Large eddies move entire cloud complexes. Smaller eddies wrinkle their surfaces. The cloud edges become scalloped. Thin tendrils peel away and then fold back in. Brightness traces the ridges where compression warms gas. Darkness traces the interiors where dust absorbs light. A calm payoff arrives. Turbulence does not simply oppose gravity. It redistributes density, making collapse more localized and more intermittent. The main number enters softly. A typical dense cloud can be about 100 light-years across, like a small neighborhood, inside a vast city-sized galaxy disk. The scale shift remains smooth. Motions inside a cloud determine individual stars, yet the cloud itself is shaped by a disk that spans thousands of light-years. A fourth scene tracks an expanding shell from a group of massive stars. The shell is a thin arc sweeping through lower-density gas. It has a denser rim where material piles up. The rim is bright on the inside and dim on the outside. The edge is tapered, not sharp. It thickens where it meets a denser filament. Behind that filament lies a shadowed pocket that stays cooler. Another small unlock follows. Feedback can compress gas at the shell rim and trigger new collapse, even while it disperses gas in other directions. The third core idea is outflow. Outflow is gas pushed out of star-forming regions. It resembles a slow breath exhaled through porous fabric, where some pathways carry more flow than others. It resembles foam rising and spilling over a cup edge in uneven streams. It matters because outflows carry energy and metals into the halo and beyond, changing future cooling and future accretion. A fifth scene widens to the galaxy's halo. Hotter ionized gas forms a diffuse envelope. Cooler streams still fall in along filaments. Where inflow meets the hot halo, a boundary layer forms. The layer is a gradient in temperature and density. It is a mixing region with curls and sheets. Some inflow penetrates, some is heated and slowed. A small payoff arrives. Galaxies can keep growing because inflow continues, but the form of inflow changes when halos heat and when feedback strengthens. A limit of observation enters softly and clearly. Internal processes at early times are difficult to resolve. Distant galaxies appear as small smudges, so disks, shells, and cloud lanes blend together. Spectral lines that trace gas phases can be faint and broadened, limiting precision in measuring turbulence and outflows. Dust complicates inference by hiding star formation and altering apparent colours. Models must separate what is intrinsic from what is absorbed and re-emitted. Different feedback prescriptions can reproduce similar luminosities, so certainty requires many constraints that are not always available. The limit remains calm, and the physical cycle stays consistent. A sixth scene returns to the disk mid-plane where dark lanes intersect. At the intersection, gas density rises. Cooling becomes efficient. A new cluster begins to form. The nearby older cluster continues to heat the surrounding medium. The result is a mosaic of states. Some regions are ionized and warm, some are neutral and cool. Boundaries are thick and gradual. Another small unlock arrives. A galaxy becomes a layered ecosystem of temperatures and ionization states, where star formation proceeds in pockets protected by geometry and shielding. A seventh scene widens to show the galaxy as a rotating whole. The disk turns. Spiral-like arcs of higher density sweep around, stretched by shear. Within those arcs, clouds form and break apart. Feedback creates bubbles that rise out of the disk, leaving cavities with rounded rims. The cavities are not empty. They are filled with thinner warm gas. The rims are denser, and they glow faintly from heating. The scale shift remains gentle. A single bubble's rim thin compared with the disk can influence gas flow on larger scales by opening channels into the halo. The closing motion eases forward. With regulation in place, galaxies can persist and multiply across the cosmic web. The next section moves outward again, following how these growing galaxies imprint the larger universe through light and matter, and how cosmic structures become more connected over long distances. The large-scale universe becomes readable when many faint galaxies imprint subtle patterns on the spaces between them. The calm answer is direct. Gravity shapes a web of density, and that web leaves repeating scales in how matter and light are distributed. A first scene opens far outside any single galaxy. Filaments stretch across darkness like pale ribbons with thicker spines. Between filaments lie wide voids where gas is thinner and smoother. At the intersections, knots glow faintly from clustered galaxies. The physical detail is a gradient. Density fades from knot to filament to void in long, smooth slopes. In that region, a signal would travel through voids with little absorption, then meet thicker gas near filaments where absorption strengthens. The first small unlock arrives gently. The universe does not become uniform with time. It becomes structured in a predictable way, with preferred separations that repeat across many regions. The first core idea is the cosmic web. Cosmic web is the network of filaments and nodes in matter. It resembles cracks in drying paint that connect into a branching pattern. It resembles frost lines spreading across a window thicker where branches meet. It matters because the web guides where galaxies form and where gas flows. A second scene narrows to one filament edge. The filament has a soft boundary where density rises over a long distance. Along that boundary, gas streams inward. The flow is layered. Faster flow occurs in lower density outer layers. Slower flow occurs near the denser spine. A small unlock follows. Filaments are not static bridges. They are moving conveyors that feed nodes and thicken over time. The second core idea is baryon acoustic scale. Baryon acoustic scale is a preferred separation from early sound waves. It resembles ripples in a pond that leave a faint ring long after the splash is gone. It resembles a subtle spacing mark on a long ruler that repeats in many measurements. It matters because it provides a standard pattern that links the early universe to later structure. A third scene shows the scale as a faint tendency. Pairs of galaxies are slightly more common at certain separations. The effect is not an obvious ring in any single place. It is a statistical halo when many regions are averaged. The physical detail is gentle. around dense nodes, an unseen shell of slightly enhanced probability sits as a broad ring-like preference, blurred and soft. A calm payoff arrives. The same sound waves that shape the microwave background also leave a ruler in the later galaxy distribution, connecting first light to present structure. The main number arrives softly. The preferred separation is about 500 million light-years. That span is like spacing between far-flung archipelagos, not like the size of a single island. The scale shift remains smooth. A pressure wave in the early plasma sets a length that later appears in the spacing of galaxies. A fourth scene moves to absorption in intergalactic gas. Between galaxies, thin hydrogen remains. It forms sheets and filaments that absorb specific wavelengths from background sources. The absorption is not uniform. It becomes stronger where density is higher. It becomes weaker in voids. The physical detail is a set of layered curtains. Each curtain has a thickness and a gradient. Light passes through and loses small portions at particular energies. Another small unlock follows. The spaces between galaxies are not empty. They hold a record of density that can be read through absorption patterns, even when the gas emits little light. The third core idea is bias. Bias is galaxies tracing density imperfectly. It resembles bright lanterns marking only the busier streets while quiet lanes remain unlit. It resembles foam on waves showing crests more than troughs. It matters because interpreting galaxy maps requires understanding how luminous matter samples the underlying mass. A fifth scene shows this in a calm contrast. In a dense region, many small galaxies cluster. Their combined light makes the region easy to detect. In a lower density region, fewer galaxies form, and the same mass contrast is harder to see. The result is a map where bright points exaggerate some features and underrepresent others. A small payoff arrives. When bias is modelled, galaxy surveys can still recover the underlying mass pattern and measure how structure grows with time. A limit of observation enters softly and clearly. Large-scale patterns are inferred from finite volumes. This introduces sample variance. The largest modes are represented by only a few waves across the observed region, so their amplitudes carry uncertainty. Redshift measurements have errors that blur positions along the line of sight, softening sharp features in the inferred map. Dust and absorption can also hide some galaxies, creating selection effects. Models must correct for these biases and for incomplete sampling. Different assumptions about galaxy formation can mimic similar clustering signals, so cross-checks are required. The limit remains calm, and the connection to the early universe stays strong. A sixth scene widens to show time layering. Farther distances reveal earlier times. The cosmic web appears less developed there. Filaments look thinner, nodes look smaller. The same pattern exists, but it is less contrasty. The gradient from knot to void is shallower. Another small unlock arrives. Structure growth can be seen as a change in contrast rather than a change in the basic blueprint, with the web sharpening over time as gravity amplifies initial differences. A seventh scene returns to the BAO imprint. In a map made from many galaxies, the preferred separation appears as a gentle bump in a correlation curve. It is not a spike. It is a broad hill with a soft slope. The hill encodes how much the universe has expanded since the imprint was set. The scale shift remains gentle. A length stamped into a hot plasma becomes a measurement in the cold, later distribution of galaxies. The closing motion eases forward. With large-scale structure patterns established, the story can drift toward how light from many galaxies adds into backgrounds that fill space. The next section follows diffuse backgrounds and the gradual build of cosmic radiation fields, linking early afterglow to later accumulated light without haste. The universe fills with background light in layers, each layer a quiet sum of countless faint sources. The calm answer is direct. After first light sets the earliest glow, later stars and galaxies add new diffuse fields that bathe space without forming sharp images. A first scene opens in a wide void between filaments. The void is not empty. It holds thin ionized gas and a faint radiation field. The field has no clear direction. It is a soft wash that changes slowly with position. Along the void's edge, a filament forms a gentle wall of higher density. The wall has a tapered boundary fading into the void over long distances. In that region, light behaves as a drifting sea of photons that can be absorbed, scattered, and re-emitted by gas and dust. The first small unlock arrives quietly. Background light is not a single thing. It is a stack of different histories with each band carrying a different origin story. The first core idea is extragalactic background light. Extragalactic background light is accumulated starlight and dust re-radiation. It resembles a distant city glow seen through haze even when individual lamps are invisible. It resembles a soft choir where single voices cannot be separated, yet the total tone is clear. It matters because it traces how much star formation has occurred across cosmic time. A second scene narrows to a region near a young galaxy. Starlight streams outward. Some of it is absorbed by dust in the galaxy's lanes. Those lanes are layered sheets with dark cores and warmer edges. Absorbed energy is not lost. It is re-emitted as longer wavelength infrared light that leaks out more easily. The physical detail is a temperature gradient across dust layers. Warmer grains sit near illuminated surfaces. Cooler grains sit deeper inside. Another small unlock follows. Dust does not only hide light, it transforms light into a different color of background that can travel through the universe with less absorption. The second core idea is spectral redshifting. Spectral redshifting is wavelength stretching as space expands. It resembles a slow stretching of a spring that widens the gaps between coils. It resembles a melody slowed down so each note becomes deeper and longer. It matters because light emitted in ultraviolet or visible bands can arrive much later, as infrared blending into a background that carries time information. A third scene widens to many galaxies across a filament. Each galaxy contributes a faint beam in many directions. Most beams never intersect anything dense enough to absorb them. Some pass through thin gas and lose tiny fractions by scattering. Where beams intersect dust, rich regions, they shift into infrared and then stream outward again. A calm payoff arrives. The background is built not only by bright rare galaxies but by many modest ones, whose light is individually faint yet collectively dominant. The main number arrives softly. The background accumulates over roughly 1 billion years in its early growth phase like a slow filling of a large basin from many small streams. The scale shift remains smooth. A single star emits light in moments. The integrated glow becomes a cosmic field that reflects epochs. A fourth scene focuses on scattering in the intergalactic medium. Free electrons remain in ionized regions. When photons pass, some scatter slightly and change direction. The scattering is subtle. It does not create sharp halos. It creates faint smoothing of radiation fields. The physical detail is a soft blur at boundaries where electron density is higher. Near filament scattering is a little stronger. In voids, it is weaker. Another small unlock follows. Even when the universe is mostly transparent, a small electron population can still gently reshape backgrounds by spreading light more evenly. The third core idea is optical depth. Optical depth is how likely photons are to be absorbed or scattered. It resembles fog thickness that determines how far a headlight beam can travel. It resembles layers of thin fabric stacked until transparency declines. It matters because it controls how much early radiation is preserved and how much is redistributed. A fifth scene turns to energy exchange between background light and gas. In low-density regions, background ultraviolet photons can keep hydrogen ionized. In denser pockets, recombination restores neutrality. This creates a patchwork of ionization fraction that shifts with the background intensity. The boundary regions are gradients, not lines. A small payoff arrives. A diffuse background acts like a thermostat for the intergalactic medium, setting a floor temperature in many places and shaping future collapse thresholds. A limit of observation enters softly and clearly. Measuring diffuse background light is difficult because local foregrounds can dominate. Emission from later structures can swamp the faint extragalactic signal, especially in infrared and optical bands. Instrumental stray light and scattered light can also mimic a background. Separating components requires careful modelling and cross-correlation with galaxy counts. Some parts of the background may come from sources too faint to resolve, so direct validation is limited. The uncertainty is not dramatic. It is a reminder that the background is a subtle quantity, inferred from many partial views. A sixth scene returns to the filament edge where a faint radiation gradient exists. Closer to the filament, the background is slightly brighter due to more galaxies. Farther into the void, it dims. The dimming is smooth. There is no sudden cut-off. The physical detail is a gentle slope in intensity across tens of millions of light years. Another small unlock arrives. The background is not perfectly uniform. It carries the imprint of large-scale structure with brighter regions near nodes and dimmer ones in voids. A seventh scene widens to the layered cosmic sky. The microwave background remains as the oldest uniform glow. Over it lies the integrated starlight background. Over that lies an infrared background from dust re-emission. Each layer shifts with expansion, sliding toward longer wavelengths over time. The scale shift remains gentle. A photon's wavelength changes slowly across billions of years, yet the cumulative effect reshapes how the universe appears in every band. The closing motion eases forward. With backgrounds established, the story can drift toward a final wide view, where early events and later structures connect into one continuous timeline. The next section moves into perspective, placing the first light and first galaxies into a calm, unified arc that settles without haste. Time in the early universe feels like a landscape where distance also becomes history. The calm answer is simple. Looking farther means seeing earlier stages, and the timeline becomes a layered stack of conditions rather than a single moment. A first scene opens as a slow glide along a filament. Near the filament spine, gas is denser and warmer. Farther out, density falls in a smooth gradient into the void. Along the spine, faint galaxies sit like dim beads embedded in the flow. Their halos overlap slightly, creating a thicker region where ionization is more persistent. The physical detail is a set of layers, a denser inner core, a softer outer sheath, a wide surrounding void. In that region, light behaves as a messenger that carries earlier states forward, while the medium it crosses keeps changing. The first small unlock arrives quietly. A single snapshot never shows the whole story. The timeline is reconstructed by comparing many slices at different distances. The first core idea is light travel time. Light travel time is delay caused by finite speed of light. It resembles distant thunder arriving after lightning stretched across enormous distances. It resembles ripples reaching the shore long after a stone falls in. It matters because a distant galaxy is seen as it was not as it is now. A second scene narrows to a patchwork map of ionization. Some regions are fully ionized. Some still hold neutral islands. The boundary between them is thick and mottled. It has scalloped edges where dense clumps resist clearing. It has smooth arcs where voids clear first. Another small unlock follows. The timeline is not a straight line everywhere. Different regions progress at different rates because density and source distribution vary. The second core idea is cosmic variance. Cosmic variance is natural differences between large regions. It resembles weather patterns where one valley stays foggy while a nearby ridge clears. It resembles a quilt where some panels warm faster than others under the same sunlight. It matters because the universe's history must be described with distributions, not only averages. A third scene shows how averages are built. Many distant fields are combined. Each field contains a different mix of knots, filaments, and voids. When stacked, their differences smooth into a coherent trend. The physical detail is a soft ring of statistics. A typical reionization fraction rises with time. A typical galaxy brightness rises with time, yet the spread remains. A calm payoff arrives. Even when individual regions differ, the global arc still emerges because the same physics repeats across many places. The main number enters softly. The age of the universe reaches about 1 billion years by the time early galaxies become more common, and rionization is largely complete. That span is like a slow century in which landscapes settle and rivers carve valleys. The scale shift stays gentle. A process that begins with photons ionizing single atoms becomes a global phase change across vast volumes. A fourth scene returns to the microwave background as a reference layer. It is smooth with tiny temperature ripples that map early density differences. Over time, those ripples grow into the cosmic web. The connection is not direct in any one image. It is a transformation in which small ripples become large contrasts. The physical detail is a growing relief map. Shallow dimples deepen, ridges thicken, voids broaden. Another small unlock follows. The early afterglow is not only a relic, it is an initial condition that predicts later structure when combined with expansion and gravity. The third core idea is growth factor. Growth factor is how density contrasts increase with time. It resembles a faint crease in fabric that deepens when the fabric is slowly pulled. It resembles a shallow groove in sand that becomes deeper as wind repeatedly follows it. It matters because it links early tiny variations to later visible structure. A fifth scene shows a gentle ladder of checkpoints. First, the afterglow sets the initial ripples. Next, neutral gas forms and cools. Next, the first stars and galaxies ignite and create ionized bubbles. Next, bubbles overlap and the intergalactic medium becomes mostly ionized. Next, chemical enrichment changes cooling and star formation. Each step leaves a different kind of imprint, and each imprint appears in different wavelengths and statistics. A small payoff arrives. The timeline can be read by matching each imprint to the physics that produces it, like matching layers in sediment to changing climates. A limit of observation enters softly and clearly. The timeline is inferred from incomplete data. Many distant sources are too faint to detect, so the census of early galaxies is biased toward the brightest. Absorption line studies sample narrow sight lines, so they provide sparse probes of a patchy medium. Reionization timing can be consistent with different bubble sizes if measurement resolution is limited. Background light measurements face foreground contamination that can dominate the faint signal. Models must connect these partial views. Uncertainty remains in details such as the exact distribution of ionizing sources and the smallest scale clumping. The limit is a gentle boundary, not a barrier. The broad arc remains well supported by multiple lines of evidence. A sixth scene widens to a panoramic time stack. In the farthest slice, the universe is simpler and smoother. In nearer slices, the web sharpens and galaxies multiply. The same filament seen at different distances appears at different developmental stages, like a river seen in different seasons. The physical detail is a changing contrast. Shadows deepen near knots, gradients steepen along filament edges, voids become cleaner and more open to long travel of light. Another small unlock arrives. The early universe is not a separate realm. It is the same expanding space viewed at different ages, and continuity is the most important feature of the timeline. A seventh scene slows and steadies. The cosmic web remains. Background fields remain. The afterglow remains. Each component shifts gently with expansion, cooling, and structure growth. The scale shift stays calm. A photon's wavelength stretches quietly over billions of years. A filament thickens quietly over billions of years. Both changes are slow, layered, and consistent. The closing motion eases forward. With the timeline assembled into a coherent panorama, the next section moves toward a soft resolution. It gathers the main threads into a single calm arc, then lets the story settle into rest without sharp edges. A calm unity appears when the timeline is treated as a set of conservation rules playing out in expanding space. The simple answer is steady. Expansion cools and dilutes. Gravity gathers and sharpens. Light records each stage in different ways. A first scene opens with a wide, slow view. The microwave background forms a smooth sphere of faint glow. Over it, the cosmic web appears as a dim relief of filaments and voids. The web is not a mesh of lines, it is a set of gradients. Density rises softly toward filaments and rises more steeply near nodes. In that region, light behaves as both messenger and environment. It carries images forward, and it also sets ionization and temperature flaws in thin gas. The first small unlock arrives quietly. The whole history can be summarized as a balance between smoothing by expansion and sharpening by gravity, with radiation acting as the link between them. The first core idea is expansion cooling. Expansion cooling is temperature falling as space grows. It resembles a warm mist that thins and cools as it spreads across a wide valley. It resembles tea cooling faster when poured into a wider bowl. It matters because cooling enables atoms to form and later allows gas to collapse into structures. A second scene narrows to the epoch of recombination as a physical boundary in time. A fog-like plasma clears. Photons decouple and stream freely. The transition is not a razor edge. It is a thick surface in time where scattering gradually drops as neutral atoms appear. The physical detail is a fading haze. Scattering becomes less frequent, so the last scattering surface has depth and softness. Another small unlock follows. The microwave background is not emitted from a point. It is emitted from a broad layer, and that thickness sets a limit on how sharp the earliest image can be. The second core idea is transfer function. Transfer function is how initial ripples become later patterns. It resembles a drum skin that filters different vibration frequencies, letting some tones ring longer. It resembles a lens that blurs some scales and preserves others. It matters because it explains why some early variations survive as clear structures and others are smoothed away. A third scene moves forward to reionization as a second boundary layer. Ionized bubbles grow around galaxies. Their edges are not smooth spheres. They are wrinkled by density clumps. Neutral pockets remain as islands with tapered borders. The physical detail is a patchy shoreline. Ionized regions form bays and channels. Neutral regions form coves and peninsulas. A calm payoff arrives. Reionization is not only a milestone, it is a change in how gas cools and collapses afterward, because a persistent background field alters chemistry and temperature. The main number arrives softly. The universe becomes about 400,000 years old when the microwave background is released like the first clear view after a long fog lifts. The scale shift stays gentle. This is a short time compared with the billions of years that follow, yet it sets the reference frame for everything later. A fourth scene returns to galaxy formation as a local expression of the same rules. Gas flows along filaments into halos. Cooling competes with feedback. Disks form with dark lanes and bright rims. The physical detail is sheer. The disk rotates. Inner parts move faster than outer parts. This stretches clouds into arcs and layers. Another small unlock follows. The same gravitational instability that shapes filaments also shapes spiral-like density waves and cloud complexes inside disks, only at vastly different scales. The third core idea is scale invariance. Scale invariance is similar behavior across different sizes. It resembles river networks that branch in comparable patterns from small streams to large basins. It resembles cracks in clay that repeat branching styles from tiny pieces to broad plates. It matters because the universe can be understood by recognizing repeating motifs rather than memorizing isolated facts. A fifth scene widens again to show the connection among backgrounds. The microwave background remains a smooth floor. The extragalactic background light builds as stars form and dust re-radiates. The ionizing background waxes and wanes as sources evolve and as gas becomes more transparent. These fields overlap in space. Their intensities change with time. The physical detail is layering in wavelength and in location. Some regions near filaments are brighter, some voids are dimmer. Another calm payoff arrives. The universe becomes a set of coupled reservoirs where radiation fields gas phases and structure, All influence each other without requiring sudden events. A limit of observation enters softly and clearly. Many of these connections are inferred rather than directly imaged. Early galaxies can be missed due to sensitivity limits, so the true total light budget must be estimated from incomplete counts. Background fields are difficult to measure because local emission and scattered light can obscure the faint signals. Rionization structure is reconstructed from sparse probes and statistical measures, so bubble sizes and topology carry uncertainty. Simulations must span enormous volumes while also resolving small-scale gas clumping, which is computationally challenging. These limits do not erase the arc. They soften the details and leave room for multiple consistent models. A sixth scene slows to a quiet checkpoint. A filament feeds a node. A node hosts many galaxies. Each galaxy cycles gas through cooling and feedback. Over time, metals enrich the gas and change cooling pathways. Dust increases and redistributes starlight. The physical detail is a gradual change in opacity. Dust lanes deepen. Infrared glow increases. Ultraviolet escape can decrease in denser systems. Another small unlock arrives. The universe becomes easier to map in some bands and harder in others, as dust and metals rise, so the choice of wavelength becomes part of the story. A seventh scene lifts into the widest calm view. The early timeline is now a single continuous thread. A hot, dense beginning expands and cools. Photons decouple and form a smooth afterglow. Atoms appear and the universe becomes dark. The first stars ignite and carve ionized bubbles. Galaxies multiply along a web. Backgrounds accumulate in layers. The scale shift stays gentle. Minute temperature ripples become million light-year filaments. Single photons become a sky-filling glow. The closing motion eases forward. With the arc assembled and steadied, the next section resolves without urgency. It settles into a soft landing where the same patterns continue, and the narrative can become quiet enough to rest. The story ends most gently when the universe is treated as a quiet continuum instead of a set of separate chapters. The simple answer is that a few early transitions set the stage, and everything afterward unfolds as a slow deepening of structure. A first scene opens in near darkness after the first atoms form. The gas is mostly neutral. It is thin and cold. It carries faint ripples in density like shallow ridges across a vast plain. The physical detail is softness. Gradients are broad. Boundaries are weak. In that region, light behaves as a traveller that mostly passes through, because there are few free charges left to scatter it. The first small unlock arrives quietly. Darkness here is not an absence of physics. It is a stable condition that allows later change to stand out. The first core idea is decoupling. Decoupling is when photons stop scattering and begin free travel. It resembles fog droplets settling so a lamp beam no longer blooms. It resembles a pond surface calming until reflections become clear. It matters because it creates an afterglow that preserves early conditions. A second scene turns to that afterglow as a pale shell. It surrounds everything. Its pattern is almost smooth. It carries tiny temperature differences as gentle mottling. The mottling is not random noise. It is a set of seeds. Over time, gravity amplifies them. The physical detail is a grain in the pattern. Slightly warmer and cooler patches sit beside each other with soft edges. Another small unlock follows. The afterglow is both a picture and a starting line because it encodes where matter is slightly denser. The second core idea is baryon acoustic imprint. Baryon acoustic imprint is a preferred ripple scale in matter. It resembles a faint ring left in sand after a wave retreats. It resembles a barely visible ripple line that repeats at a consistent spacing. It matters because it leaves a measurable pattern in how galaxies later cluster. A third scene moves forward to the first starlight. Small halos gather gas. Cooling allows collapse. The first stars ignite and emit ultraviolet light. Ionized bubbles appear around them. The bubbles are not perfect spheres. Their edges are rough. Dense knots make darker peninsulas that resist ionization. Voids clear first and become bright channels. The physical detail is a scalloped boundary. It has a thick transition zone where neutral and ionized gas mix. A calm payoff arrives. Rionization is not a switch that flips. It is a growing network of bubbles that slowly overlaps until transparency becomes common. The main number enters softly. The first clear afterglow releases when the universe is about 400,000 years old, like a long simmer that finally stops steaming. The scale shift stays gentle. A few 100,000 years is brief compared with billions of years, yet it sets the reference for everything later. A fourth scene widens to the cosmic web. Filaments stretch between nodes. Gas flows along the filaments with a steady inward drift. Infall heats some regions and cools others through expansion. The web has thickness. Each filament has a denser spine and a softer outer layer. Around it, the void is smoother and colder. In that region, light behaves as a probe whose path depends on what it crosses. Some wavelengths slip through. Others are absorbed or scattered by remaining neutral pockets. Another small unlock follows. The timeline can be read as a set of filters where each era changes which signals can travel freely. A fifth scene slows into a single lingering image that gathers the arc. A vast translucent shell of afterglow lies behind everything. In front of it, a patchwork of ionized regions spreads. Between them, filaments thread like pale smoke. Along the filaments, faint young galaxies glow. Their light is softened by distance and by intervening gas. The physical detail is layering. A bright core fades into a dim halo. Dust in some galaxies forms a darker lane that slightly reddens the glow. A calm payoff arrives. The universe becomes understandable when the same three ingredients repeat. Expansion sets the overall cooling and dilution. Gravity sculpts the web. Radiation links the two by heating, ionizing, and recording. A limit of intuition and observation enters softly and clearly. Many early steps are reconstructed indirectly. The faintest galaxies remain below detection limits, so the total population must be inferred from brighter samples. Neutral hydrogen is traced through absorption signatures that sample narrow paths, so bubble sizes and topology carry uncertainty. Background light levels are hard to separate from nearer foreground emission, so estimates depend on careful subtraction and modelling. Simulations must cover enormous volumes and also resolve small gas clumps so compromises are unavoidable. These limits soften exact timings and small-scale structure. They do not remove the broad sequence of transitions. A sixth scene moves into the present universe without urgency. Structure continues to grow. Galaxies merge and rearrange. Voids expand and become emptier. The same patterns remain visible only with stronger contrast. The scale shift stays calm. What begins as tiny ripples in a nearly uniform plasma becomes filaments and clusters over billions of years. A final small unlock settles in. The early universe is not a distant myth. It is the same space in earlier conditions, and those conditions still shape what exists later. A seventh scene becomes quiet and slow. The afterglow remains as a faint background. The web remains as a dim architecture. Ionization remains as diffuse state in intergalactic gas. All of it changes steadily without sharp edges. In that region, light behaves as a gentle thread tying time together, because travelling outward also travels backward in history. The closing motion eases into rest. The arc has no abrupt ending. It simply becomes still enough to be held as a single, continuous panorama. The next moment is only the same expansion continuing at the same calm pace.